Well, good afternoon, everybody, and Len can relax a little bit now. Thanks very much, Len, for giving a really excellent talk. Len's let me off because I only really have to talk for an hour, and I don't intend to talk for any longer than that, really. And I'm going to give a much more of an overview talk, really, about Nano Dielectrics without going into quite so much detail. So I suppose it's always difficult with these sessions to know what sort of level of detail is appropriate for the audience. And so I'm trying to make this a fairly introductory session on Nano Dielectrics. So perhaps I should start off by saying what a Nano Dielectric is. We could say that the word it is a neologism, which I'm sure that Michel Frochetto, I can see there, was likely to include, because the French hate inventing new words, and they think it affects their language too much, and so they invented this word neologism to describe any new words that come into the dictionary, which they didn't like before. So fractals were another example of this. But we could define, I suppose, a nanodielectric typically as a conventional dielectric material, often a polymer, or it could be other materials, but it's typically a conventional dielectric material, which I'll refer to as the host during this afternoon, into which we've put some filler particles with a size of perhaps a few tens of nanometers, perhaps a bit less than that. And we could call those nanoparticles. And so we've got a well-dispersed system containing nanoparticles inside a host material. And it's assumed that the system is better if it's well-dispersed. One might speculate whether it would have interesting properties, actually, if it wasn't necessarily well-dispersed, or what really that means. All I'm going to consider this afternoon are host materials that are solid and polymeric. One could certainly consider putting these nanoparticles into fluid materials, specifically oils, for example, but I'm not going to particularly consider those today. And so I'm going to consider solid polymeric host materials with nanoparticles in. Well, I suppose that's the usual type, at least for high voltage insulation. So what's the structure of my talk? Well, I thought I'd start off by talking a little bit about why we might need nano dielectrics at all, and then talk about different types of nanodielectric, in fact different types of nanoparticle really. The effects of introducing nanoparticles into a host material. What would we expect that to do, and what might be the effects on the electrical properties of those materials, and why might those be useful for us in an engineering sense? And finally, I'd like to give you some possible applications of nanodielectrics in an electrical power system. So let's kick off then with why we might need nanodielectrics at all. Well, I'm going to give an example here of submarine power cables, because this is an area I suppose I've been in for a long time. And these power cables, this is a three-phase power cable system, carry huge amounts of power, and I expect quite a few of you are involved in these, although you may not be. Obviously, dielectrics covers a huge area of study. But when you consider that each of these cores can take thousands of amps, and that each of these polymer insulations can withstand thousands of kilovolts, you're talking about, and in a three-phase system, you're probably talking about a good three-phase cable, perhaps carrying away all the power from a reasonable sized power station. So the implications of that are that you want it to be reliable, because if it does go down, an awful lot of lights go out. It has to carry high powers, and obviously it still has to be relatively competitively priced. And in future, we're going to be considering cables supporting DC rather than AC stresses. But when you start to look at this, this is a good example of how things have developed over the last few decades. You can see that the average electrical stress on a power cable has increased higher and higher, and indeed we've been moving to higher and higher voltages, as well as thinner and thinner insulations. And currently we're working around 10 to 14 kV per millimetre for power cables. And it's quite conceivable that we could be getting up towards 20, 25 kV per millimetre, but that will probably require some new materials. So perhaps you can start to see where I'm going, in the sense that if we're going to need new materials, then what new materials have we got in line for that sort of thing? Because power cables at the moment are pretty much all polyethylene. Yes, so sorry, this is giving you some of the insulation thicknesses starting to reduce down as well. Well, as part of this sort of case study into power cables then, let's have a little digression into high voltage DC. And Giovanni this morning had a technical committee of the Dielectrics, Electrical Insulation Society. I think the first meeting, which was on high voltage DC, to try to define what the work of that committee will actually be. And at the moment, nearly all power transmission is by using AC. And AC, of course, has the great advantage that we can use transformers at either end of the line. So we have a generating source, we step up the voltage using a nice, efficient, relatively easy to build, well-known transformer, we stick it down a power cable, and at the other end we use a transformer to do the opposite and bring the voltage back down to what we want. And this is good, because transformers are nice and efficient, but unfortunately AC cables are rather lossy. And certainly just the capacitance of the cable gives us a great deal of headache when this cable starts to get very long, because there's an awful lot of current going through the cable that's simply charging up and discharging this capacitive cable 50 or 60 times a second. But if we go to DC, we don't have any of those losses to speak of in the cable. We have a bit of ohmic loss in the conductor, but nothing much else. And so we can make the cables very, very long. But the problem with this is we then have to use AC to DC converters, and these are relatively inefficient, not compared with transformers. So you can see that for shorter distances, the AC is more efficient. You have a small amount of transformer loss, but not very much. But then the cable is relatively inefficient. Whereas for longer distances, DC is more efficient. You have a larger amount of converter losses, but the cable itself is much more efficient, much less lossy. So what's this got to do? Where am I going with this? Well, this is related to what Len was talking about as well. In an AC cable, the voltage at any point within the cable is defined by the capacitance of the cable. And so you can work out the voltage distribution across an AC cable in terms of the permittivity. But since the permittivity is relatively independent of anything, it's relatively independent of temperature, for example, and it doesn't really change with age, then you can be pretty certain that the potential distribution across your cable is pretty well defined at any time in the future. On a DC cable, you can see that the voltage depends on the resistivity, or the conductivity if you like, of the cable. And so this is much more problematic, because the conductivity is highly dependent upon temperature, and there's going to be a temperature distribution across the cables. And furthermore, we could have space charge. I've shown some in red glorified space charge being ejected from the centre here, and that is also going to affect the potential distribution quite dramatically by the presence of this space charge, and therefore the voltage is going to be quite difficult, and the fields are going to be quite difficult to predict inside these DC cables. So if you look at voltage across the cable, you can see that if the field drops nice and linearly from one side to the other, that is going to be the case when we don't have any space charge. But if we introduce some space charge, then there's going to be very little drop of voltage inside here, and so it's pretty well all going to be dropped there, and the field magnitude of the electric field inside the cable is going to be increased by the space charge. So AC cables, the field's controlled by permittivity. The permittivity is roughly independent of temperature and applied voltage, so the field is reasonably constant throughout the cable. DC cables, the DC field is controlled by the conductivity and the space charge accumulation. The conductivity is highly dependent upon temperature. The space charge is highly dependent upon applied voltage and indeed time as well. And so the DC field could vary considerably, and a very high field, of course, can lead to breakdown. And so if that's, I don't know if I want to go through this, but it's difficult to see here anyway. But in a cable without any space charge, we might expect the field enhancement to look something like that. Whereas with a little or a lot of space charge, you can see that the field distribution is quite different. So the reason I've put that in is that that is another reason why we're going to be looking for new materials in to insulate our power cables. Now, of course, we're also looking for new materials for a plethora of other systems as well. For example, capacitors, or indeed for cable terminations, for local distribution systems, and so on and so on. And typical problems that we have with high voltage insulation is our electrical breakdown, and this can occur as a result of aging and degradation, partial discharges, electrical treeing, and so on. And electrical breakdown in DC systems, particularly associated with space charge accumulation. And also, we may well experience practical problems associated with tracking and flashover. Well, Len's talked quite a lot about polyethylene this afternoon. Just to remind you, this is a nice, simple polymer, one might think, especially when you look at the nice, simple formula. It's just a repetitive load of ethylene mers to make this polymer of polyethylene. But of course, and the reason I suppose that it's chosen is that it's relatively cheap. We could convince ourselves that it's too cheap, because certainly the sort of polyethylene that we use for cables is not particularly cheap. If you take a drum of polyethylene, perhaps weighing about a ton, you'll pay several £1,000s for that if you want a super clean material. So it's not all that cheap. It's not like polythene bags, that you buy from the supermarket to put your sandwiches in. But at least it can be made in this super clean way, and clearly the manufacturers have put a great deal of effort into doing that. It can be cross-linked, and I think that's probably one of the real advantages of using polyethylene. And in cross-linking, the chains of the polymer have cross-links which basically form sort of ladder-like formations, so that the chains are linked by other chains that link them together. So a cross-linked polyethylene cable is really one big, huge molecule in one sense, in the sense that all these polyethylene chains are actually linked together with each other. And this is typically done in cables by heating it up and using a chemical reaction to do that. But of course the nice thing about that is that it doesn't then melt. So although polyethylene itself melts at just over 100 degrees Celsius, once we heat up a cross-linked polyethylene, it becomes more like a gel. And it's not actually going to allow the two conductors to sort of move together. Of course, if you heat it up too much, it'll start to go black colour and eventually catch fire and do nasty things like that. But we could take it very close to its melting temperature without any bother. And a couple of quite important other points that it's got going for it is that there's been a huge investment in polyethylene. Although you might not think that's very important, if you go around a cable factory or a polyethylene factory, you'll realise that there's a huge amount of money gone into making the material in the right way. And simply to suggest, from a laboratory that we might change it is quite difficult. So of course, there's quite a lot of confidence in the users. But there are problems because it's unlikely to be reliable once we get above perhaps around 25 kV per millimetre, and certainly some of the effects that Len showed us with space charge packets and so on are starting to occur even below those. So certainly we'd expect space charge injection to be occurring probably below 25 kV per millimetre, even in a good scenario. It's going to be susceptible to space charge accumulation, partly because it is such a good insulator, and partly simply that it's very difficult to have very much current flowing through it, and so that's going to be very difficult for high voltage DC systems. And it's not very tolerant of defects. So if we have any protrusions from the electrodes into the insulating material, then it's relatively easy for electrical trees to grow. Or if there are contaminants in the polyethylene, again we could get field divergence, and pretty well any contaminant in polyethylene is going to be more conductive or have a higher permittivity, and therefore give us an enhancement of electric field. And also voids that may occur in the polyethylene will also quickly initiate discharges which lead to electrical trees. So what could we do to change then? So if we've run out of options and we still want to increase the electric field, or we want to make it more reliable, then what can we actually do? And I'm sure that there are other stories one could tell for lots of other electrical components that you can think of in the high voltage area. One thing you might argue that you should do is not to fill it with all these nanoparticles, because after all, filling a material with nanoparticles, well, surely that's likely to increase all the problems that we have with defects and all the rest of it. So why don't we simply change the chemistry? And indeed, perhaps we should be thinking about changing the chemistry as well as perhaps introducing nanoparticles. And so, for example, this is a butyl acrylate. And you could imagine that you could include this as a block copolymer with polyethylene. So you can have some of the polyethylene and then a block of butyl acrylate. And this is being tried out by Borealis, and it's quite widely publicised, so it's in the literature, so I'm not telling you any secrets there. And people have tried other blends as well. I believe that Alan Vaughan is going to be talking later at this conference, I haven't read his paper yet, on Nano Dielectrics. But Alan is certainly a great advocate of also looking at changing the chemistry. So if we want to advance polyethylene, one thing we could do is to sort of change it rather than just substitute it for something completely different. And that is likely to lead to a change in the macroscopic properties and probably change the morphology of the polyethylene. And so we could well be changing the sort of conduction mechanisms and probably the chemical trapping mechanisms that one might see in this sort of material. But another thing that we could do, apart from changing the chemistry, is to add fillers. And so I suppose that when you start to think about it like that, we could either do something to do with the chemistry or something to do with the physics. And I suppose adding nanoparticles or other particles changes the physics somewhat. Otherwise, we move away to completely different materials altogether. So I said, why do we want nano dielectrics? And I think the reason is that it's the only thing you can do if you're not going to change the chemistry, or you can do both. So let's have a quick look then at different types of nanodielectric. And these are really quantified, apart from changing the host materials, by the different types of nanoparticles that one can introduce. And a way of thinking about this is how many dimensions they've got. So if we think about adding three-dimensional particles, then we're probably talking about quasi-spherical type particles. But we could add nanoparticles that are essentially two-dimensional, so essentially platelets, and typically these might be layered silicates. And if you've ever wondered why clay moves in the way that it does, it's because it's made of these platelets, and it'll very easily squash and move around, rather like graphite does, give you a slimy sort of constituency, I suppose. And you could think about adding one-dimensional particles, sort of, I call them whiskers, you know, like cats have whiskers, and these might be typical carbon nanotubes that are the obvious ones there, but some of the metal oxides will also form these sort of whiskers as well. So, three-dimensional nanoparticles typically having an aspect ratio somewhere around 1, perhaps 1 or 2. These are silica ones here, and silica ones were probably the first ones that we really played with. Partly because silica is already used as a filler in many epoxy systems, although not necessarily, of course, at nanoparticle sizes. So if you look at a typical epoxy that's used for, I don't know, sort of bread and butter, low voltage insulation systems, often in low voltage distribution systems, then it's often coloured red or something like that. Then it's often full of sand, basically, and indeed it's almost sand stuck together by epoxy, and so there'll be a lot of silica in that. So it was unsurprising that silica was one of the first fillers to be used. It can be produced using the Sol-Gel process, quite reliable for nanoparticles, and we can functionalise or compatibilise the surface of those, and I'll say a little bit more about that in a minute as well. And typically we're using low volume fractions of these materials. I put 1 to 20%, but perhaps probably typically around 3 or 4%, something like that. Other metal oxides, hydroscopic, so relatively easy to disperse in polar polymers. We could use titanium dioxide, which we could also make into whiskers if we want. Magnesium dioxide, aluminium oxide, which is also common in epoxies. Aluminium oxide's been used in larger particles to control the thermal conductivity. So one might argue that it could be good where we want to do that. And zinc oxide. Zinc oxide's conventionally been used because it's a sort of semiconducting material. If we move to two-dimensional nanoparticles, These are often called nanoclays, and I couldn't find a very good diagram of these, but essentially we form these SiO4 tetrahedral structures, and these are normally bound together with metal cations, and so they could be dispersed quite easily in hydrophilic polymers, and unless the clay is made to be hydrophobic. And you can see that there are two obvious types of ways of doing this. One's called intercalated and one's called exfoliated. And here in the intercalated ones, we still end up with this sort of fairly regular structure of the particles themselves, which are simply intercalated by, in this case, the polymer chains that run in between. Or they could be completely exfoliated, in which case the polymer chains in between might still be cross-linked and so on, and subject to their own sort of chemical reactions. So intercalated is this sort of pilled structure here, still well-ordered multi-layer structure. Exfoliated, we have complete separation of the clay lamella and a continuous polymer matrix that goes in between. And I'm assuming that if I'm going to put these slides onto the conference website at some point later on, so you'll have these various references to look at. Finally, one-dimensional nanoparticles. Well, the obvious thing here is to jump on a bandwagon and use carbon nanotubes. Of course, they have exceptional mechanical and thermal properties. You can make them as conductors, insulators, or semiconductors. So you should be able to make them field-dependent. But there are problems. They aggregate very easily. And one would assume that if you're going to put in relatively conducting one-dimensional structure into a nice, beautiful, well-insulated, low permittivity host material, then you're likely to have some problems with field enhancements at the end of the materials. And as far as I can see, less work has been done incorporating these very high aspect ratio nanoparticles into the host materials than many of the others. So what would we expect the effect of introducing nanomaterials into a host material actually to be? Well, let's just go back and revise our polymer morphology. If we take the polymer chains, then these can bend, and we can bend them backwards and forwards, and make them into lamella. So lamella are sheets of crystalline areas of polyethylene, which Len was talking about with holes and flowing through them and so on. And so these are likely to be relatively thin sheets, I suppose, up to a few tens of nanometers thick, perhaps a little bit more. They could be quite wide. They could be a micron or several microns wide in their other dimension. And one could argue, in fact, that polyethylene is itself a nano dielectric. I don't know whether Michelle would agree with that, but it's actually got these in, which are, in a sense, nanoparticles. They're the crystalline nanoparticles of polyethylene in a host matrix of amorphous materials. So in a funny sort of way, polyethylene is almost intrinsically a nanoparticle in itself. Sorry, a nanodielectric in itself. It's quite well known that you can look at the spherolytic structure of polyethylene, and this one that looks like a sort of Turner picture, or Van Gogh perhaps, picture of a, I don't know, what do you think it might be? A sort of close-up of a sunflower, I don't know. But shows you all the structure that you can see in polyethylene. This is 10 microns across here. And so these are the lamella. You can see them sort of edge on there, being quite thin and stretching up for several microns across. So what would we expect to happen when we put in nanoparticles? Well, if you put in a particle into something that's going to crystallise, usually one of two things happens. One thing that might happen is that crystals might form on the defects that you've introduced into the material. So you might expect crystals to grow from the material that you've put in. However, if you're coming from a semiconductor point of view, you might think, well, that's not actually what happens in, say, in a silicon system. What tends to happen there is that any defects get pushed out of the crystal. The crystal tends to grow and push all the defects out of it. So what actually happens in polyethylene? Well, unfortunately, it depends, is the answer. And it depends very much on how you grow it. So the disruption to the crystallinity strongly depends on the processing method. And although these have got different first authors, they're both done at the University of Southampton. And you can see that in this case, the crystallinity is much, much more disrupted than it is in this case here. And in this case, these are platelets, these are the layered silicates of clay that I was talking about. And you can see them if you look inside. I don't know if you can see them there and there and there and there and there and there. They're just evenly distributed but through here. It's really had no effect whatsoever on the crystalline structure of the material. Whereas here, we've had a lot of disruption, and I suggest that's because the polyethylene is trying to grow its crystals from these platelets, and then it immediately finds another platelet. And so you get loads and loads of little bits of crystals which are not very well defined. So you'll have to read the papers if you want to understand more about that. But what I'm trying to say is that it very much depends on how you actually process the material. And I'm not actually going to say very much about manufacturing and processing these, partly because I'd be bluffing because I don't know very much about it. And there are other people in this room who know a lot more about it than I do. What else would we expect to happen then when we put in nanoparticles? Well, this is taken from a paper by John Lewis, which he published in 2004. He was actually, about 10 years before that, he published a paper talking about what might happen if we used nano dielectrics. And I don't know if that was probably the first paper in this particular subject area. He assumed that the host material might behave a little bit like a fluid electrolyte, really. What I've tried to draw here, he drew this, I've tried to redraw it a bit, is that over here, this is the nanoparticle, or part of the nanoparticle surface, and this is the host material over here. Now, if we take something like silica, we've got a lot of positive charges going to be available on the surface, and we therefore expect that to attract a lot of negative charge from the host material. And so we'd have a fairly regular, well-controlled layer on the surface, which, borrowing the term from electrolytic chemistry, is known as the Stern layer. And then further away from this, we sort of get a double layer effect, where you can see we get an excess of negative charge, and then gradually it starts to mingle up. So we get a less ordered region over here, which is sometimes known as the Gilly-Chapman layer. It's a sort of diffuse layer here. And if you plotted the charge density of ions and counter-ions and co-ions, you'd probably see something like that. So you would expect that from a charge point of view, you'd get some effect on the host material right around this nanoparticle. And this is known as the interaction zone. So around these nanoparticles, we're going to have some sort of effect, which is really quite difficult to define, which is generally known as the interaction zone. Here I've drawn some big particles, And you can see that the interaction zone is there relatively small around these big particles. I don't know how big these particles would be, but perhaps around 100 nanometers, perhaps getting on for a micron. But if we shrink these down, you can see that the relative size of the interaction zone is much bigger than it was. So the particles are now relatively small compared with the interaction zone. And if we go down to nanoparticles, of course, you won't be able to see them anymore because they'll be too small on this projector for you to see. However, if we look at this little bit up here, just to prove that I have drawn them in, I can enlarge it and you can see that they are actually there. So they're the nanoparticles that we can see. And we can't see in this picture. But if I now introduce the interaction zone around these nanoparticles, what do you suddenly see? You suddenly see that nearly the whole of this material is now filled with interaction zone. So the effect of the nanoparticles is that they're starting to have an effect on nearly all the material due to this interaction zone. And this interaction zone is actually quite large. Here's a map of Bologna. So you can see the nice sort of ring road goes around the old walled city here. And if you took about 1 cubic metre of a typical nano dielectric and you worked out the surface area of all the nanoparticles inside there, then it would be roughly this size. It would be roughly the size of Bologna. So you can see that the specific area of a nano dielectric is huge. The amount of area surrounding all the nanoparticles in 1 cubic metre of nanodielectric, if you open them all up, would fill something like the size of Bologna. So you've got an awful lot of area there and an awful lot of interaction zone to play with. Of course, one of the problems is, and if we wanted things to do after this, would be to try to think about how better we could characterise that interaction zone, possibly directly using physical or chemical characterisation, possibly indirectly by perhaps generating computer models of what we would expect it to do, and then doing some experiments to see if they do follow the computer models, or perhaps by using secondary experiments such as dielectric spectroscopy, where we try to work out what we would expect the macroscopic response of such a system to be. So these interaction zones, as I said, might make it more crystalline, or they might not. They might attract water. I'll tell you about that a little bit more. Well, they might change the dielectric properties, perhaps allowing some sort of percolation, electrical percolation, perhaps between these various interaction zones. Only a small concentration of particles are actually required to approach the percolation limit. And this is an approximate thing here, but if we took, say, 4% of volumetric concentration, and we had some 10 nanometer radius particles with an interaction zone of 10 nanometers, then we'd actually be at the percolation limit, despite the fact we've only got 4% of these particles. Right, you would expect, for example, for spherical particles to require about 19% to reach percolation. So you can see you'd have some big effects for relatively small concentrations. Now, I did mention water, and there's quite an amusing story that back at the end of the 19th century, the end of the 1800s, there was a posh hotel, I think it was the Savoy in London, decided that it was going to stick mirrors all over its bathroom. It used an equivalent of an epoxy to do that. It was that sort of thing. It looked really good, and they were very proud of their new bathroom. And then this, presumably I like to think of it as some lady walked in there, very posh person walked in there and ran the bath, and of course filled the room up with humidity. And it's unfortunate for the Savoy or whatever it was that the epoxy much prefers to hold on to water than it does to glass. And so instead of the epoxy sticking the glass all over the walls, it stuck the water all over the walls, and all the glass crashed onto the floor. So we know that we have a problem there. And indeed, if we make boats out of fiberglass, which we do, then we know they don't sink, and the reason for that is that the epoxy has to have some sort of, sorry, the glass has to have some sort of treatment. It might be a silane treatment, which means that the epoxy prefers to stick to the silane treated glass than it does to the water. And for example, this is a molecular dynamics simulation of water. This is the gold here, the silica in blue, and the epoxy in red. And these are snapshots every 450 picoseconds. And you can see that very quickly this red epoxy comes away from this blue silica, and the water interjects itself in between. So it's very important to be able to functionalise these materials. And indeed, I did some work with project student Chen Zhu, where we put some silica nanoparticles in epoxy without any functionalisation at all. We did it later with functionalisation. And if you just take the epoxy material and you change the relative humidity, the epoxy itself will increase in mass by about 2.5% as it absorbs water. However, if you put large particles in, it actually absorbs less because the particles replace most of the epoxy. If you put small particles in, these are 3 nanometer diameter particles. Sorry, this is 3% weight of particles. You can see there's a lot of water is absorbed around the particles. And so the overall increase in weight, increase in uptake of water increases quite a lot. And if we go up to 9% weight of these particles, then we can increase quite considerably the amount of water uptake. And from that we can actually work out roughly what the shell thickness of water around these particles is. And at 100% relative humidity, we get about 3 nanometers of water surrounding each of these particles. So you can see it's important to have some sort of way of functionalising or surface treating these materials to control and indeed to define the interaction zone. And you could use silane. Clive Reed, for example, with Keith Nelson, has been trying out lots of other more interesting exotic materials as well. For more information on manufacturing and surface functionalisation, I could perhaps recommend this book, which is on dielectric polymer nanocomposites, which you could at least have a look at the contents on Amazon and see whether you think it's of interest to you. What are the effects then on the electrical properties? Well, let's first of all start off by having a quick look at conduction and polarisation. So, going back to these 50 nanometer nanoparticles of epoxy, 9% by weight, 4.5% by volume, with water shells, we'd expect these to increase in conductivity because we're now above the percolation limit, or at least very close to it, and we therefore expect to see quite long-range movement of charge through the water surrounding the particles. If we only have a 3% by weight, that's 1.5% by volume, then what we see is we still could have some movement, but it won't occur right throughout the material. And so we might expect to have some sort of quasi-DC type behaviour here. And if we had larger particles, perhaps without any overlap, we might expect, you can't see it very well here, but you might expect to see charges accumulating here. So negative and positive charges, and perhaps giving us Maxwell-Wagner polarisation. And indeed, if we look at the dielectric properties of the first system, the 3% weight one, where we have limited, we're below the percolation limit, we actually do see quasi-DC with parallel slopes on these bone plots of real and imaginary capacitance at low frequency. If we silinate that, however, we don't see that anymore. We actually see that the real part is now flat, and the imaginary part still has a slope of -1, a slightly lower level, and what we're basically with is the conductivity of the host material. And if we look at the micro-composites, then we actually do see the typical Maxwell-Wagner behaviour with a slope of -2 in the real component and -1 in the imaginary. What about electrical treeing then? What would we expect to occur there for a start? Well, electrical treeing probably has two mechanisms going on it. One is that inside these tubes we'd expect to have electrical discharges. And we know that because we can see it. We can see light being emitted from the electrical trees. But what about at the end of these tubules? What we would expect then is to have a solid state avalanche, perhaps for 2 or 3 microns or so in front of that tree, which starts to degrade the polymer in front of that. And that then allows the next branch to form. So what would we expect nanoparticles to do to this process? Well, we might expect it to interfere with avalanche effects. Nanoparticles might help to prevent electron avalanche occurring and help us to prevent electrical treeing. And here's a little approximation so that you can see roughly how far apart nanoparticles might be. So here's a cube, and I've tried to divide that into 3 by 3 by 3 cubes, so 27 little cubes, and I've put a nanoparticle occupying one of those cubes. So this nanoparticle occupies 1/27th of the space, which is about 4% by volume, which is perhaps a little bit higher than we normally need to find. And so the distance between these cubes is about twice the width of the particle. Now, of course, you can go another way and say, well, it's a bit longer than that. But what I'm trying to say is that in a typical nanocomposite, nanodielectric, then perhaps the typical distance between the nanoparticles is 2 or 3 times the width of a typical nanoparticle. So not very far, actually. So we've got a nanoparticle that's only sort of 10, 20, 30 nanometers across. The distance between the nanoparticles probably won't be much more than 100 nanometers at the most. So what effect would that have on an avalanche process? Well, in an avalanche process, what we have is we start off with an electron going at a fairly high speed. In the case of the electrical treeing, it's probably the result of that discharge inside the tubules. It smashes into an atom, which knocks off another electron, and when that's picked up enough speed from the electric field, it smashes into another atom, those produce 2 more, and so on. And so you can see that after a few generations, in this case 1, 2, 3, 4, 5, we've got lots and lots of electrons all going through the material at very high speed. So that's our avalanche. But what happens now if we introduce some nanoparticles? Well, you can see that this one here, this electron, instead of smashing into another electron, has smashed into a nanoparticle, which I assume stops it. Don't know exactly what happens, of course, but it could be argued that it's not going to be generating secondary electrons anymore. This one has had the luck of the draw and has smashed into another one, but again, they keep hitting nanoparticles rather than other atoms. So the secondary emission from these is greatly reduced. And therefore, we might expect that we could generate a nanodielectric in which avalanches are substantially reduced. And therefore, we might expect to see a reduction in electrical treatment. And certainly, work by Keith Nelson and so on, where he talks about voltage endurance, whereas in fact he's actually growing electrical trees really in these materials. he's shown that with nanoparticles, the expected lifetime is much greater than with equivalent microparticles. And there's other work by, for example, IMI here. There's quite a lot of papers you could find where the insulation breakdown time due to electrical tree is substantially increased in the case of nanoparticles. I'm running a bit out of time, so we do questions at the end, is that right? What about electrical breakdown then? Well, you can really prove what you like with electrical breakdown and nano dielectrics, and you can see that some results are better and some results are worse. And that doesn't really surprise me because there's lots of different breakdown mechanisms. And so I think that what you really need to start to do is to start to think about the breakdown mechanism. So if you're trying to prevent thermal breakdown, which you might be in high voltage DC, for example, then you might want to look at a way of controlling the thermal conductivity. If you've got avalanche breakdown, then I think probably that, provided you've got good dispersion and you haven't got field enhancements, then you may well be able to do that. A lot of breakdown is likely to be defect initiated due to protrusions, voids, defects and so on. And it may be that we could give the particles some sort of control of the electric field. So as the field goes up, we have a more conductive material, and therefore that might reduce defect initiated breakdown. Electromechanical breakdown, I don't know. Don't know if I've thought about that before, but if we could increase the mechanical Young's modulus of the material, then perhaps we could do something about that. But of course, ultimately, particles might also introduce weak points into our systems, and so we've always got to play one of those against the other. In terms of space charge accumulation, there's not been too much work on that. This is some work that I did with Keith on titanium dioxide. And what I've done here is actually plot the maximum field intensity. This is across a lump of polyethylene. I think it was about 150 microns thick, so Len can guess where it comes from. And the average electric field was just over 4 kV per millimetre. You always get a little bit more than that because it's never quite regular, especially at the interfaces. And so with a nano filler, it was just a little bit higher than that. With a micro one, the PA showed that we got charge accumulation, as one might expect, and the charge accumulation increased the maximum electric field. It almost doubled it, actually. And one again might think, well, if you've got interaction zones that perhaps are slightly more conductive, perhaps they're changing the way that that charges can extract themselves from traps and so on. Pre-breakdown effects was a whole series of papers, and again I've put these in here so that if you get hold of this presentation you can look at them yourself, by Javaberg et al. And I was her external examiner for a PhD this year, which is why I know about this series of papers. But they're quite interesting. I don't always agree with the analysis of their results, but the results themselves are pretty good. I won't take you through them all, but there's one, for example, here which is on pre-breakdown effects. And what she's done, and this is just a sample of results, is looking at electric field strength versus current density, the sort of things that Len was talking about earlier on. And perhaps I'll come back to that. Len was talking about the effect where you might have ohmic behaviour at low electric fields, then perhaps becomes a square law, perhaps doesn't, depends on your assumptions, then becomes proportional to a higher power voltage, and ultimately, if it hasn't broken down by then, which is highly unlikely, goes back to a lower value when all the traps have been filled up again. And this was first published by Chuti and Barrow. I've redrawn it a little bit to try to illustrate those points. And Javaberg identifies an E to the naught region, which is not true really. It's just that she can't measure the currents at that point at all. She starts to measure it here, and it becomes ohmic, and then she has a higher power region, and then possibly a square law up there. And she looks at the 3 thresholds for this. So this is really irrelevant because it's just the point at which her measurements become possible. But this is quite an interesting one. This is where it changes from ohmic behaviour to a trapped charge behaviour. And so if we look at a reference material, this doesn't contain any nanoparticles, we see that it breaks down once it goes above the ohmic region. But essentially it doesn't have a second threshold. So all we see is this e to the power 1, this Ohm's law behaviour. It actually, she reckons, has a slope of 0.7, but that's probably not bad in terms of a result. But eventually breaks down at 368 kV per millimetre. If you now look at this, she's actually looked at changing the chemistry as well as introducing nanocomposites. So this is polyethylene with butyl acrylate, which is the system I showed you earlier on. And she doesn't then see, this is 6% weight with no functionalisation for dry and wet materials. This is functionalised dry and wet. For the no functionalisation, she doesn't actually see any ohmic behaviour, and it just goes straight into into these trapped trapped behaviours. For this material, which is functionalised, she does have the ohmic behaviour, and then she gets an e to the power 3 law, and eventually breaks down at 440 kV per millimetre, which is substantially higher than the reference material. However, as she points out here, it's only based on 3 samples. And unfortunately, because the voltage was so high, she couldn't actually measure this very easily. So what I'm trying to say is that you'll have to read the papers if you want to find out more, but this has a big effect on the pre-breakdown, and because of the charge trapping behaviour of these materials. So I've borrowed this from Tanaka and Imai's paper. We can see that partial discharge resistance is generally enhanced, tree lifetime is generally prolonged, space charge may be reduced, tracking resistance could be enhanced, breakdown strength don't really know. They've been very polite and put increase or no change, but I've seen it decrease on many occasions as well. Permittivity can be either, and that's because the interaction zone tends to determine the permittivity behaviour. Dielectric loss is complicated, and DC conductivity can go either way as well. So what about possible applications for this? And to make my life easy, I've completely borrowed their paper now from not quite the latest version of the Electrical Insulation magazine. This was the one that came out in January, so this is the paper by Tanaka and Imai. And I've done it because I really love this diagram that they've got here of a transmission and distribution system showing all the different values that you could do that. So if we look at the top left of that, you can see that generator widening could be an epoxy nanocomposite, and of course the primary substation could be the same. We could on the pylons be using silicone elastomers with nanocomposites. If we move down the bottom, we could see that the DC cable insulation might be polyethylene. It might be polyethylene with a co-polymer with a nanocomposite. And looking down the right, we've got various motors which could have enamelled wire with nanocomposites on. You'd have to really make sure it was well distributed because, of course, they're very, very thin. The capacitor insulation may well contain nanocomposites and the polypropylene. And I like even the fact that the epoxy, the carbide have epoxies in it as well. So I hope that gives you a very quick whiz through some ideas for nano dielectrics. And as I say, there's quite a lot of literature out there to read. So thank you for inviting us both. I know one or two people have questions, but perhaps we take those offline afterwards. I'll hang around for a little bit. Is that all right? Because I know, I'm sure others want to go and get ready for the session at the end. Unless you do want to ask questions, I don't know.
If you want to talk to us about this presentation and you don't want to speak up now, you can try and buttonhole us later in the conference. Can't promise that we've always got the spare time because people grab hold of you, but if we have, we'll try and